you cannot do something but just to start with something, some plan that you have in your mind. Right? And then when you come to lecture, then you verify. Okay. Okay, again, we will continue on with the kinematics because, again, as I said, I hope to get you the theories in and then you practice it. I want you to practice it. I wanted to actually go through 3, but I know if I don't give you time to practice, you cannot practice. I will give those 20 you want to practice it. So we'll discuss this next Friday. So you have at least a week to start playing around with the questions. Okay, if you really don't understand, you can look at the book, the textbook, and see how they do it. Then we come for class next Friday. I'll go through my thought process, why exactly I do this. Okay. Okay. Now for the next half of the lecture, we'll talk about forward and inverse kinematics. Now, lecture 3 cover the basics. Okay, rotation matrices, transformation matrices, how to find the inverse, forward, whether you need to pre-multiply, post-multiply. All these will come in play in this lecture. Okay. So again, kinematics, there is forward, there is inverse, right? We talked about that when we started lecture 3. Now, whenever you have a particular, let's say a robot or any manipulation system, maybe a mobile robot or industrial robot, doesn't matter, you will always look at your task space. You will have position and orientation, right? Same thing. Many people, academicians, have a variety of ways to represent. Right? I'm not going to share everything too much, but I'm just going to share a few ones that will get you started. Right? There are a lot of other methods, and these will be the methods that we will be testing you on. Right? So we break it up into position and orientation. Now, just to put things in perspective, whenever you are doing some task, let's say for industrial robot simulator, you need to do some task somewhere here, right? What you will do is this: you will usually use the first 3. Let's say if it's a 6 degrees of freedom robot, right? You have 6 parameters in a task space. By right, you only need 6 degrees of freedom for a robot. You can properly arrange that to reach that particular pose. Pose means position and the orientation that you want. If you do it lesser, 5 degrees, 4 degrees, you will not be able to reach all your 6 specified parameters that you want, 3 position, 3 orientation. If it's more than 6, that means there are many ways to reach that particular pose that you want. But you will realize if you are really the one who's looking at more than 6 degrees of freedom robots, you will face the issue of what is the optimal solution to select. Because you got more than one solution, you need to run another optimization algorithm to select the best option that you want. Right? So seldom in the industry that they use 7, 8, 9, no, 6 is the max. Right? There are cooperative robots like the Baxter robot that I showed you earlier on. These are actually upcoming only, but I'm not too sure how prevalent they will be in the industry because it's like a human arm. Controlling will be very, very challenging. Right? But let's see how they progress. Let's see how they go. So in this lecture, we will look at 3 ways to identify your position and 2 methods to identify your orientation. So again, if you need to do some tasks here, some manipulation tasks here, you will use the first 3 joints, go to that particular position first. Then you will use a wrist, dexterous wrist or N effector to do the fine task. Right? So it's always this kind of combination. I do the cross motion first, then the fine motion. Same thing, so that's why I'll go through the position first and then the orientation. Now again, I was telling you between kinematics is between input and output. Forward is I input in the joint angles. okay, this motor move this by this amount, this motor move by this amount, then you reach to some position in your task space. Right? That's forward. Straightforward. Actually. If you are doing the inverse, you are given, and most of the time you are doing inverse because you want to go to this position. You only know that I want to do task here, but I don't know what joint angle should I have in my robot to go here. That is why each of these methods will have their inverse kinematic solution. Right? Okay. Again, as we go, some of them are straightforward, some of them are a bit tedious, but you have to memorize. But there are some tricks to remembering them easier. Okay? Okay, this one is something we have done. We know forward kinematics, you know the joint angles, you input the angles to the motors, output is where the end effector will be. Inverse is the other way. Okay, remember this, sometimes you in the exam, they may ask you to find the inverse kinematics, then you happily do some forward kinematics. You will not get the points you want. If you want to remember it in an easier way, you can say forward is straightforward. It shouldn't be much calculation, just plug in the values, you will get the answer. Then inverse is the slightly more tedious one, which you will go through. Right? But in order to find inverse kinematics, you will use the forward kinematic equations and then determine your inverse kinematics parameters. Okay? Again, if I want to move to this particular location, what I will do is I'll make the robot move to this position first, and then I will do some orientation in this position. Okay? This is a general strategy. Right? Okay. Yeah, these are the few things I will go through. Okay. For position, I will share with you 3 ways of doing your position, or kinematics for position. Okay. The first one is Cartesian coordinates. Remember Cartesian robot? Straightforward, all are linear stages. Right? These are all prismatic joints. So what you do is you will just type one. Let's say you want to. Okay, all these robots are 3 degrees of freedom. Just looking at position. That means you just want to reach an X, Y, Z position. That's it. Orientation should not change. Take note. Okay. Now, because these are prismatic joints, you can see it's quite straightforward. If I want to go to a particular X value, I will just input some X value in this prismatic joint, it will go to the X point. If I have some Y value I want to go to, I will just input some value to this prismatic joint here, and I'll go to the Y point, and likewise for Z. So, the forward kinematics is, okay, this is just pure translation, right? So you won't have any rotation matrix, so that's why it is identity matrix here, right? And this is the px, py, and pz, the location that you want to go to. Okay. Right? Now, inverse kinematics is this. I want to reach XYZ locations. What are the joint or the prismatic lengths I need to input to the system? Because everything is prismatic actuators, it's straightforward. Inverse kinematics is whatever value they give you, that is the value you are going to use in your actuator. And you reach that point. Okay, this is Cartesian coordinates. The most simplest one. Exams, depending on whether you will specify whether Cartesian or cylindrical or spherical, you will go through next. Okay? So basically, what you want is this. I want to go from this my origin of my robot, I want to go here. Done. The second one is called a cylindrical coordinates. Why? Because it forms like, if you look at mathematics, there are different types of coordinate systems that you can use. Polar coordinates, you can call it polar for this as well, or cylindrical. So it's the way you specify your location in your volume. What this one does is this: it will have some radius you can specify to, some angle you can specify to, and then maybe another height. So if you look at the workspace of this kind of robot, it's like a cylinder, right? But Compared to this, these are just XYZ, just positions. If you look at this, two are so-called lengths, one is an angle. Whereas for previous one, all three are lengths. Okay, this is the difference. Take note. So, how this thing works is this. First step is you will always do your radius first. How much I want to go out first. Second step will be how much I want to rotate by alpha. Third will be how high I want to go, L. Okay, so with that you can reach a particular position, XYZ. Right? Okay. Again, you notice this. Now, sometimes if you are just doing translation, you will just call it TRANS. It means that we are just doing pure translation. Right? And they will define it like this, R00. That means the R means that you are doing something about the x-axis. Okay? That's why you see the R at your EX here. The rest are 0. There's nothing being done to the Y and the Z component. Okay? So that's why if you look at this matrix, is identity matrix and R00. Right? There are some meaning to this. Now the second thing you are doing is rotation about z-axis by alpha. Pure rotation, no translation involved. Right? So that is why if you go back and look at your notes, your lecture 3 notes, this is similar to your rotation about the z-axis. And because this is pure rotation, origins are coincident, nothing happens, so it's 0, 0, 0. Okay? Third step is I'm just doing a translation by z. They call it translate 0, 0, L. First term, x component 0, second term, y component 0, third component is a z component, which is L. If you look, pure translation, identity matrix, 0, 0, L. Okay? My question is this done using fixed frame or multi-frame? You look at your steps, this is step 1, this is step 2, this is step 3. What are you doing? Pre or post? Pre means fixed frame. See, so this is something I can also observe from the way they tell me the position. Okay. So when you kind of add all these things up, right? You multiply them together, you will get this final matrix. What did I tell you earlier on? That I'm just looking at position, right? If I'm just doing pure position, sometimes I got some terms in the orientation matrix. Notice that something is not right. Okay? Okay. What happens is this. When you do certain motion, there are some undesirable motions, couple of motions that happen. So they somehow also inadvertently orientate the frame. Right? That is why we have this unrotated forward kinematics. Which means I will rotate back the matrix, the frame, such that the axes are parallel to the ground frame. Okay? And you will do a rotation by your A-axis. A-axis is what? X, Y, or Z? Correct, Z, Okay, by an angle, negative alpha. Okay. You notice, they post multiply this. I can also, if I happen to forget, whether post or pre, you see, I'm doing things with respect to the moving frame. A. That should be another indicator to you that I should post multiply. Some transformation there. Okay? Okay, I'm just kind of sharing some observational tips. Okay? If you do this multiplication, then you come to this final matrix. You realize that, again, it's back to identity matrix, and then you have your EX, EY, EZ. So that is the form that we want. Okay. So this is your forward kinematics for a cylindrical coordinate. Remember about this portion, the compensation. Okay. This is the thing you need to take note. Okay. So what happens in forward kinematics? What do we input? For this scenario, what are the three parameters? Radius, yeah, L and your alpha. These three. You input in this, you get your transformation metric. Right? Straightforward. What if I give you a transformation metric? Okay, what if I give you a transformation matrix, or I say that I want you to go to this particular point? Okay. Now remember, this is your T cylindrical, which is some identity matrix. This is your unrotated. Okay, I was purposely put it unrotated because I've already done the compensation to align the final transformation, the frames to your movable frame so that they're all parallel, just like your pure translation. Okay, so I have identity matrix 0, 0, 0, 1. Then you have R cosine alpha, R sine alpha. Okay. In order to cut things short, if I put C alpha, it just basically means cosine alpha. S alpha, it just means sine alpha. Okay. Just to keep notation short. Okay. And you have your L. L. Okay. Now, what is inverse kinematics for positions? What information am I given? The final location, right? That means I will be given P, X, P, Y, P, Z. This is what I'm given. I need to find my R, L, and alpha. Okay, I'm given this. I need to find this. Right? What will you do? Before me going further, what will you do? I've given this. I have this generic equation. What can I do? Anybody? Okay. I've given this. I know these variables in this moment. What you will do is comparison. From this, I can come up with three equations. Ex equals to R cosine alpha. Py equals to R sine alpha. Pz equals to L. Okay. So for Pz, straightforward. Now, for Px, Py, I got two equations, two unknowns. I know this. I know these two. I don't know this R and alpha. What can you do? What is tangent alpha? What is tangent alpha? Sine alpha over cosine alpha, right? Can I rearrange these equations? Let's say I put R sine alpha, R cosine alpha, and this is equals to cy over ex. Am I making sense so far? Right? You are using your equations doing comparison because you know some zones you need to find answer. Usually, if you have x number of unknowns, you should have x equations for a determinate or definite answer. Okay?
What is it?
Okay. Here, I want to share with you another thing. How many of you remember this quadrant that we call it CAST? You remember? Right? A means all these angles are positive. If your cosine is positive, and maybe yours and all other, because you need, what you need to do is this: you need to identify which quadrant does your angle lie. Right? So it's not just one answer. You need to look at your coefficient, whether this dx dy is positive or negative. Okay? So your tangent alpha will have two, your so-called your alpha, which is your up tangent. You will have two answers. Okay? Now R will always be positive. Right? It's from 0 onwards. You cannot go negative. Right? Your radius is always 0 to positive. So this will always be a positive term. So that's why you can determine the signs of your cosine alpha and sine alpha. Okay? Let's say my sine alpha is positive, my cosine alpha is positive. Where will my angles lie? Both are positive here and here, because my what? How would you do it? You got done it before, right? Go on. Every angle, if you do okay, if there are always two sets of an angle when you either do a sine, cosine, or tangent. They will give you the same value. You always need to find two sets of angles. Okay? So if you want to look at it in a way, it's like if you see both are positive, one is definitely here. Then your tangent alpha, it's positive also, right? That means your other answer will lie here. That means you have one angle here, then you have another angle which is 180 plus. Okay? So this is the thing you need to take note of. You need to look at the relations between your equations, because if you say whatever angle I have for alpha, if I do a sine, if I do a cosine, it should be positive. Okay? So take note of this. When we go through the example, then I will go through it a bit more detail. But just take note of this first. Okay? So there may be two answers, there may be. And then sometimes some answers may invalidate because they are maybe beyond your physical limit. Right? Okay? So just take note of this in mind first. Then we will go through it. But just take note that in order to solve your alpha, this is what you will do. You will do a comparison first. Okay? Okay. The third one, which is getting a bit more trickier, is spherical coordinates. This is a bit different because you have one length term, which is r, and two angle terms, which is your beta and gamma. Okay? And essentially, you still want to go to a particular position. Same thing, you will do a translation about your z-axis, followed by rotation about your y-axis by angle beta, followed by rotation of about z-axis by gamma. Okay, and this is what you get. Again, because of this orientation, you get a lot of unwanted orientation effects, but you only are interested in position. So you have to do your unrotation. But this one is a bit, because there's two angles, you have to unrotate two angles. You will unrotate by axis, about axis 0. By negative beta. O is what? In reference to y-axis, right? NOA, right? And then followed by rotation about the a-axis by negative gamma, which is your reference to your z-axis. Okay. So why do I keep saying rotation? What does that mean to you? I hope that you will get that. Okay, let's say if I talk about rotation O minus beta, why I keep emphasizing that this is in reference to the y-axis? Because this will give you your rotation matrix, which is a rotation about y. Okay? So when you have, so it will be like cos negative beta 0, 1, 0, 0. This is cos minus beta, sine beta, so minus sine of this stuff. Check. Yeah, negative is here. Okay? That's the negative sign. So, whenever your angles have a negative, make sure you put a negative angle. Okay? So, that is why I keep emphasizing you need to look at what they give you and try to identify what does it refer. Then you can start using the basic elemental rotation. Okay? When you do a so-called unrotation for spherical coordinates, yes, for your orientation you get identity matrix. But if you look at your px, py, pz, a bit more complicated, right? But what we will do is the same thing. Okay, if you look at your unrotated matrix, you have your I matrix 0, 0, 0, 1. You have R sine beta, cosine gamma, R sine beta, sine gamma, R cosine beta. Right? And then you are given your Px, Py, Pz. Basically, what you will do is by comparison. Okay. Okay. How you will start off with this? You see, between this and this, you can eliminate two parameters. Which one are they? R and beta, right? Not really sign up, but the parameter. So what we get, tangent gamma is sine over cosine, right? Then if you just put R sine beta over R sine beta gamma, right? You are getting basically Py over Px. Okay. So with that, you will find maybe two values of maybe gamma 1 equal to gamma 2. And then you start working backwards with this. Once you know this, then you can start to find your okay, sorry, this is one. The other one is R cosine beta is your once you find your gamma, you can reduce these equations. So will be r sine beta will be dx over cos gamma r okay. So you've got two equations. Two unknowns. Okay. You will start. Yeah, okay. Alright. Don't worry about it because if either one, then you also have your r cos beta equals to your pz. From this you can look at tangent beta, which is sine beta over cos beta. But this will be both r, which is dx over cos gamma over z. Okay. When we do the example, then you will see how I will go about solving it. But remember, this is how you try to decompose it and solve it. So once you find your gamma, your beta, you just input it in the last equation to find your r value. Okay. To verify your answer is correct, your r value must be positive. Okay, positive. Okay. So after this, you do this step, maybe you get 2 beta, then after the last part is your r. Is either pz or cos beta. Okay, if we do the exercises, you will understand better. But this should get you started on doing exercises in the first place. Because even if you cannot find 2 answers, don't worry, just find 1 answer first and just proceed. Right? You will get 1 set of angle, just proceed to solve the other values. Later on, I will go through the detail of how you use this to find 2 sets of angles, 2 sets of answers. And then verify which is the right answer. So far, okay? I know a lot of mathematics, but no choice. It's still the fundamentals of robotics. Okay? Okay. Again, these 3 approaches that I shared with you today, just for orientation, for position. There are a lot of other approaches, right? But these are the only 3 that will be tested. For orientation, there are also a very systematic way of getting your orientation. Again, for orientation, it's a bit tricky. You must follow the sequence. You say I'm going to do about x-axis first, then y-axis, then z-axis. You must follow this. If you do it in any other way, and if you happen, let's say, let's look at this now. Let's say now I use example a row pitch yaw. I have these sets of solutions already made. Then I don't follow this sequence. I do some other sequence. I don't follow this rotation by N, O, or A. I do something else. And I use that solution that they have given me. You're not going to get it right. Because this thing is very dependent on how you move, and you have to follow how you move it exactly as you specified. Only then you can use it. Okay? So I know some of you, I think almost all of you are shocked the amount of equations, but there is a way to remember them. Okay, we will only look at 2: roll, pitch, yaw, and Euler angle. Okay. Now, just to share a brief quick history, Euler angles, what I'm sharing you is just only one type. There are other 11 types. So this guy Euler will be very, very free. So it's greater of 12. Okay, it's a permutation of XYZ, ZYZ, and a whole list of things. Right, it's just seeing which axis you want to move first, followed by the next, followed by the third. Okay, now this is what we do for roll pitch yaw. First, we will do a roll or rotation about the A-axis. A-axis means refers to the Z, yeah. Okay, this is what you see, yeah. Then after that, they will do a pitch about the O. O is the Y. And then the last step is yaw about the N-axis, which is the X. Right? You see the way I put it, or the way it has been put, right? Is I'm not saying X-axis, Y-axis, Z-axis. I'm talking about A-axis, O-axis, N-axis. These are what? Moving or fixed? Moving, right? So that is why you will both multiply. Right? It's step 1, step 2, step 3. That's why I say if you know your basic matrices, everything else will get simpler. Just remember the basic matrix. That's it. Sometimes what happens in the exam questions is if they're kind, they say that just prove this transformation matrix. They will say, okay, this robot did move about this x-axis, move about this moving y-axis, move about this fixed z-axis. Prove that the final transformation matrix is so and so. Okay, can be in that format. So all you need to do is just make sure you put in the right rotation matrices, multiply them. The carelessness comes in when you're doing this multiplication, right? So you can either, so what you do is this, you can either do this first and then you multiply with this, or you multiply these two matrices first and then you multiply this. Up to you. You should get the same answer. Okay? The order you multiply, but don't go and swap this. If you, instead of putting this on the left side, you put it on the right side, then because sorry, that is totally, conceptually you're wrong with it. Okay? When I mark, I look at the process. Okay? I don't focus on the final result. So let's say I happen to see that, hey, you did this correctly, you put in these right values, just that you made some error somewhere here and didn't get it, you will still get marks. Right? If you get this one wrong, then I cannot give you any marks. Okay, I know some tricks. You know, we'll just put, let's say to prove this, right? Just put this, then after that, dot, comes this. These are we know, you never did this. Okay, yeah. Technically, yes, you got the first few points, but the center portion has been marked. Right, we want to see some form of multiplication between this. Okay, we want to see some intermediate steps. Not to be every intermediate step, but we want to see some intermediate steps. That will tell us, that is how the marks are being allocated. Because there's a bit more of effort, so we still give you points. Right? But doesn't mean you do this, and then dot, the final answer, you'll get all your full marks. No, okay, I clearly highlight this here now. Alright, so give me some intermediate steps. Either you multiply this with this or this with this, then you put dot, it's okay. Okay, got my hint. Okay, save time. Work smarter. Don't need to give every step, fine. Give me some intermediate steps. Okay, so when you do your multiplication, this is what you get. Wow, damn complicated. Okay, this is your 4 kinematics. I give you my angles. You just input in this matrix, you get your transformation matrix, your 4x4 matrix. When you're doing inverse, another story. Okay, another thing I want you to take note. Sometimes the question don't have, they will never specify whether it's roll pitch yaw or Euler. How to identify? In an easier way. Have any of you all seen your exam papers, past exam papers? Okay, focus on the symbol. If you see this side A, O, N, it's talking about row picture, okay? Unless the examiner want to screw you up with that, but generally no. So far, if you use this symbol, it's row picture. If you look at Euler's, it will always be eta, sigma, psi, and this symbol, okay? So it's standard. If you see these three symbols, is Euler. If you see these three symbols, right? These three is row picture. Okay? Take note. Okay. What is inverse kinematics again? What are you given? Sorry? All the final orientation, right? You are given the final orientation. So this final orientation will be just three angles. You are supposed to find all the joint angles. These are the joint angles. So it can be row P sure or Euler. Okay, below is the next one. But what they do for row P sure is this, to reduce the complex. Again, they use the same way, by comparison. Okay, but this time instead of giving given px, py, pz, you will be given like a rotation matrix, right? N, O, A, N, Y, and Z. Okay, you'll be given this. This is the final orientation that you have. You are supposed to find all these three angles, the joint angles that you meet that final orientation. Okay, it's the same game. We just do comparison. But to reduce the comparison complexity, what they do for row P sure is they bring. Okay, if you look at this equation and the previous equation, you notice that your rotation about a-axis go over to the other side. Okay. So what they do is this: they will pre-multiply with the inverse of the a-axis rotation matrix. So on your right hand side, this inverse of this times this rotation matrix equals to identity matrix, right? Like 1, basically. So you're left with the other two matrices. Then you multiply this inverse of rotation matrix with this row P sure term that you have. Okay, and what you will start to do is you will do comparisons from this side to this side to this side. You see certain things like N. See this? There are some. This is what you are given. Okay, your row, this RPY is actually this. This matrix. But because I bring in this rotation matrix, that's why it's in this format. Don't think that this is the format that been given to you. This is something that you have to know. All you know is this NX, NY, your AX, AY, OY. Those are the things that will be given to you. Okay, this element information. But by bringing over this matrix, you notice that some of the terms you can do is in comparison. Okay, but this is not so straightforward. Again, I need to emphasize that we will still need to go back to this CASD because there will always be a few sets of solutions for your angles. When I go through the example, you will understand more. Right? Okay. It's actually just equating both sides of these matrices. How do I get this? You look at the first element. 2 dash 1, this, look at this. Sorry, look at this, sorry. See, that's why I say I also look at. You look at this and you look at this. This whole thing equals to 0. Right? Okay, so I have ny cosine A minus nx sine A equals to 0. Right? Everybody clear so far? By comparison, you look at the 0 here. This equals to this, huh? Right? Now, if you do a tangent, this is different, huh? You don't. All this is just one equation. This equals to ny over nx, right? Which is equals to tangent. So your is inverse tangent ny over nx, which is this one, right? Now you can also have both negative, you still get the same value, right? That's why they say, that's why they are looking at two variants, where ny and nx are both positive and where ny and nx are both negative. Okay? So you'll get two sets of angles to work with subsequently, yeah? Okay, for this one, they are looking at this term and this term. Okay, this over this is tangent, right? And then these terms are, because you already found your psi A, so you can just put in this value in this, right? So this over this. Remember this negative sign, you go in here, right? Then they will do an inverse tangent to this. Okay, for the second solution is your third element, third row. You look at your first element, first row, first column on both sides. Is cosine psi 0. That is what one term is. The other one is your third row, first element, which is your negative sine O. Okay. This is what you are going to do through a tangent of this. And then you get this solution. The third one is if you are looking at your second row, second element, and then the one beside it, right? Your cosine sin n and minus sin n. It's just these two terms. You do a tangent and an inverse tangent. Okay, so you look at the simpler terms and then you extract that out and then you find the solution. Right? Okay, so far about the derivation, the example we'll go through it, how to solve it. But I want you to understand this first, how they derive this. And it's easier for you to understand all this. So far, okay? Okay, the next thing is Euler angles. Now, Euler angles, they will do a rotation about your A-axis first, then your O-axis, and then your A-axis again. It's different now, it's not using X, Y, Z. Okay, if you look at it, it's a Z, Y, Z. Okay, A, O, A. Whereas for the previous one, they use A-O-N, they use all three axes. Whereas for Euler, he only used two axes, but still can be done. That's why he has the 12 commutations of his Euler angles, the 12 Euler. Just teaching you one. Okay. Again, with respect to your moving or fixed frame. Moving frame. Okay. Then that's why you will do a post multiplication. Again, remember, make sure that you know which basic notation matrix to input in. Okay, multiply them this, then you get this. Now, I just want you all to just take either one of these as a home exercise to see whether you can derive it. It's just for you to practice matrix multiplication. Okay, just take it as you know you have the answer. How can I go about getting the answer? That will help you in the learning process. Okay. Again, if they give you this kind of symbol, automatically it should be Euler angles. Sometimes they specify, sometimes they don't. They will just say, "Oh, I'm giving you this. You have these parameters. You go solve, or you get this transformation matrix." Right? So you gotta be careful. So just teaching you some smarter ways to do it. Same thing, they brought over the first rotation matrix to the left side to simplify and to do the comparison. Again, same thing, if you look at this, the first one, they are using your second row, third column elements. This thing, AY cos psi minus AX sin psi equals to 0. Then you get tangent. Right? Now because your AY, AX, you don't know, both can be positive, both can be negative, so you have two answers. Right? For this second term, it's between this one, and this one, yes, your sine and cosine. Okay? Right? You look at your sine and cosine, simple terms. And the other one will be your sine psi, cosine psi. Okay? You want to know how they're comparing, look at your right hand side, look at the simple terms. They're just equating the simple terms to get your tangent. Same thing, Same thing as this one. You just look at those with the simple sine or cosine and then use that to evaluate. Okay. And if you look at these simple terms, what they will contain is a previous answer that you have found. So you have to find this value first, this angle first, and then you can use it for your subsequent answer. Okay. But they are following a similar approach to doing this. Question? Any questions so far? Today is quite taxing. I will declare that. But once you start doing the examples, things will get a bit more simple. Okay, thank you everybody.